friends, under discussion was a DC position control system. I think it will be in order if I review the DC position control systems. This being a very important plant, very important system as far as control systems are concerned, because many of the loads are actuated by a DC motor, and a position or speed control system becomes important. So, let us see what were the basic components of a DC position control system. The basic component we have taken a motor. Let me say that here is a motor which is producing a torque Tm. Okay. Now, this motor is driving a load, and I had taken the load through a gear train. This is my gear train. By gear train I mean that it could be more than a set of gears. I have taken 2 gears pictorially, but it depends upon the torque magnification and speed reduction requirements. So, naturally it could be more than a pair of gears, it could be 2 pairs and so on. So, on this particular gear I have the load, and the 2 parameters of the load we had taken were JL and BL. Okay. Let me say that as far as this system is concerned, theta m, omega m is the velocity and theta m is the position of the motor shaft, and here in the opposite direction obviously theta L is the position of the load shaft, and the disturbance torque is going to oppose the motion, and therefore Tw I am giving this direction. So, in this particular case the conclusion of our earlier discussion was that the load parameters could be reflected onto the motor shaft. I will revise the result for you directly. Hopefully, you recall the derivation. This system, as far as mathematical equations are concerned, is equivalent to the system I am going to draw here. This is the motor. Motor produces the torque Tm, and the position is theta m. You can equivalently couple a load directly to the motor instead of showing through the gear train. I take this as the direct load. Now, what are the parameters of this direct load? Recall our derivation. I call it as J equivalent is the equivalent inertia on the motor shaft, B equivalent is the equivalent frictional coefficient on the motor shaft. In that particular case, these two will become similar, that is the mathematical equation describing the system will be the same if I write J equivalent as a function of JL, and let me say that the motor shaft has got the parameters Jm and Bm, where Jm is the friction of the Bm is the frictional coefficient on the motor shaft, and Jm is the inertia due to rotor, gears and other things. So, if I take N1 and N2 as the teeth, and small n is taken as equal to N1 by N2 as the gear ratio, in that case please recall the result. J equivalent onto the motor shaft will be given by Jm, the moment of inertia on the motor shaft, plus an equivalent portion reflected from the load shaft, and that value is n square JL. Okay. So, it means the equivalent moment of inertia on the motor shaft could be taken as Jm plus n square JL. Similarly, equivalent viscous frictional coefficient could be given as Bm plus n square BL. Okay. And the motor equation then can be written as the motor equation, the torque developed by the motor equal to the inertial torque J equivalent theta m double dot plus B equivalent theta m dot. Now, you see that theta L is not appearing in the equation at all. If you want to get the value of theta L, then naturally theta m and theta L are related by the gear ratio. So, from theta m you can go to theta L, but as far as the basic equation is concerned, the basic equation is available in terms of theta m, which is the displacement of the motor shaft. Okay. Now, if you remember the derivation, I pose a question to you. Tell me what will happen to this particular load torque on this equivalent model NTW. This please note that if Tw is the torque on the load, this is the actual torque, the disturbance torque. On the equivalent model we have seen, you will naturally write it opposing the motion. It is NTW, I am sorry, where N is the gear ratio, and therefore, the complete mathematical model becomes Tm is equal to J equivalent theta m double dot plus B equivalent theta m dot plus NTW. You will please note that Tw is the actual disturbance on the load shaft, and N is the reflection factor of that disturbance onto the motor shaft. This is very convenient, and in modeling normally we will do that way only. That is, all the load parameters, all the parameters of the gear train will be reflected onto the motor shaft, and a mathematical equation on the motor shaft will be written. Okay. Now, in addition to this, last time I had taken up the derivation of the DC motor. I think a review of that also will be in order before I take a complete position control system, and this is my target for today. I am going to explain a complete position control system to you. So, now again you take the motor, some newer points, some points will come which have not been covered in the last lecture. I had taken this as an armature controlled motor. So, in this particular case, the control variable is the armature voltage EA. I had directly neglected the armature inductance, because this is usually the case. In the approximations which we make in modeling, the armature inductance is normally neglected. So, I have not included it right in the beginning in my mathematical model. So, EB is going to be the back EMF on this. Okay. Now, let me write directly, assuming that on this motor there is a load through the gear train. However, now I am equipped to write this load directly over here, and I can drop the letters equivalent also, if you understand. I will say that J and B are the parameters of the load on the motor shaft. Equivalent word, equivalent subscription I am avoiding, because now it is clear to me, if I am taking a load on the motor shaft, naturally if the load is through a gear train, the reflection on the motor shaft will have to be taken. So, J and B are the equivalent parameters, and as far as disturbance is concerned, let me take this as the disturbance as NTW. Okay. So, in this case Tm and theta m are the two parameters of interest, because this is the torque produced and this is the displacement of the motor. I tell you that after some time you will really not require the differential equations. You will be able to write the block diagram model directly from the schematic diagram of a system. Make an attempt here itself. Just see that your input is EA, the armature voltage, and this is being opposed by the back EMF, and therefore, let me use an error detector here to represent this particular phenomena, that is, the back EMF opposes the applied voltage. The net voltage appearing across the resistor is EA minus EB. So, naturally 1 over RA, if I put a block over here, this gives me armature current. So, let me call it IA. Now, this action plan is coming directly through a block diagram. This may please be noted. This is armature current, and if I multiply it by a torque constant kT, you recall your torque is proportional to the product of armature current and field current. So, in this case what I am doing is I am taking the field constant. Okay. You will note this point please here. You have motors, DC motors, which are permanent magnet motors or wound field motor. So, if in the wound field motor, if I give a constant voltage supply, the field is constant, and for the permanent magnet motor, you can naturally take that the torque produced is directly proportional to the armature current. So, the block diagram I am going to give you is valid for both the wound field motor with constant field current or a permanent magnet motor. This point may please be noted. So, after this particular block, I have got the torque. So, let me take this variable as Tm. So, this Tm variable is going to be opposed by the disturbance torque. So, let me put a plus sign here and a minus sign here because it is in opposition. This again I think I have overemphasized my point that this is only an algebraic quantity. It could even add to Tm, it depends upon the nature of disturbance. Even if it adds to Tm, it is a disturbance, because we have not designed our system for with that objective in mind, or with that variable taken in that way that it adds to the it adds to the applied torque Tm. So, let me write here T and Tw, and therefore, this becomes the total torque available for driving the motor, for driving the rotor of the DC motor. So, here the opposition is coming from the load, and let me say that 1 over Js plus B is the load transfer function, where J and B, well, obviously it should be clear now, are the reflections on the motor shaft. So, the output here is omega, the speed. Now, this omega you have to lift from here, because there is a feedback, and the feedback phenomena is through the back EMF, and therefore, let me put a constant Kb here. So, this is going through the constant Kb into this error detector. Now, if the output of interest is position and not speed, in that particular case you will put a block here, an integrator 1 over S, and therefore, the output in this particular case will become theta m. Theta m is the output, the position, and Ea is the input armature voltage, and there is a loop inherent in the system because of the back EMF, and this loop is the back through the back EMF constant Kb. Okay. Now, if I take up this particular block diagram and I am interested in the transfer function model of this system, you see that it is a 2 input 1 output system. Let me apply superposition and set one of the inputs equal to 0. Let me set disturbance equal to 0. So, I have a transfer function between omega and Ea, or between theta m and Ea. So, between omega and Ea, please help me, I am sure you are equipped with this now. Yes, can you give me directly? See if I can write directly. Kt by Ra divided by Js plus B plus Kt Kb by Ra. This I am writing after using the basic block reduction rule to this particular loop. Just see that it is between omega and Ea. The point to be noted here, that is why I am repeating this point, you see that Kb is adding to the B term. B is the mechanical friction in the system due to bearings, due to gears, or due to any other mechanism, and Kb is adding to this term, and Kb, it means really you can say that is adding or giving damping to the system. More or less, can we use the word as if it is electric friction? Because if you require damping in the system, Kb is helping in that, it is adding to the damping, and equivalently I say as if Kb is providing the electric friction, so that the total friction is given by this B plus Kt Kb by Ra. Okay? And this particular transfer function I can now interpret in the standard form, this being a first order system. In the standard form, this is going to be equal to Km, the gain of the system, divided by tau ms plus 1, where tau m is the mechanical time constant, and that will turn out to be J divided by this quantity, which can easily be calculated. Okay? So, this is the transfer function model, and now if you want the transfer function between, let us say, theta ms over EAS, between the position and the input voltage, what will happen? A factor S will come over here. So, this theta ms over EAS will become equal to Km divided by S into tau ms plus 1. This becomes the transfer function if position is taken as the variable of interest. Okay? Now, a point in this particular case which needs mention is the correlation between the variables Kt and Kb. An important point, please. Kt is the torque constant and Kb is the back EMF constant. Okay? I want to establish a relationship between the two, and what is the use of that relationship, that also we will see. Look at the power developed. Power P is equal to EB into IA, watts. This is the power developed in the machine, EB is the back EMF and IA is the armature current. Now, let us look at the units. This I can write as KB, yes, omega into IA. What is KB? KB is volts per radian per second into radian per second into amps. Well, the unit is watts. Now, give me the equivalent expression of power developed, please. Power developed is also given by, assuming that there is no loss, assuming neglecting losses, is also given by the torque Tm into the speed omega, again the units watts. The torque Tm developed by the motor into the angular velocity omega. Now, let us look at the units. The units in this particular case are Newton meter into radian per second. This is in watts. Okay. Now, interpret this, I will keep it here, interpret this in kT terms. This can be made equal to kT into IA into omega. This is equal to, what is kT? kT is Newton meter, yes, per amp. This is your kT, Newton meter per amp. You can look at the block diagram also, that will also give you the same thing, into amp into radian per second. This is in watts. Okay. Now, please see that in this particular case, if you compare this, I hope this is also available on the screen, this expression volts upon radian per second into amps is watts, Newton meter per amp into radian per second into amps is also watts. So, naturally, if I take kT in the units Newton meter per amp, this becomes equal to kB when taken in units volts per radian per second. This point may please be noted. This point needs your attention, that if kT is taken in Newton meter per amp and kB is taken in volts per radian per second, then the numerical value of kT must be equal to that of kB. The units I am stressing, because if you take different units in that particular case, the two may be related through a constant. It is not necessary that kT is always equal to kB, it depends upon the units. Consistency of the units, compatibility of the units has to be observed. So, if I take these units, I have proved to you that if kT is in Newton meter per ampere and kB is in volts per radian per second, in that particular case numerically the value of kB will turn out to be equal to kT. It is a very important result in the sense that if you are modeling a motor experimentally, you can visualize this situation. Conducting an experiment to measure kB is much easier and more accurate than that to measure kT. I think, well, you can think what type of experimental setup will be required to measure kB. It is so simple. You will be measuring the back EMF and the speed to get you the value of kB, while in this particular case torque measurement will be required, and therefore naturally the measurement of kB is more easier and may turn out to be more accurate, and therefore even to get the value of kT you will conduct an experiment for measurement of kB and use this relationship to get the value of kT. This is an important point, and you have to keep in mind that with suitable units, taking consistent units, the two constants are equal numerically. Okay. Now, well, armature controlled motor we have taken. Just for the sake of completeness, a quick result on the field controlled scene could also be given. What will be the field controlled scene? IA is equal to constant. You will like to keep the armature current constant, and you will vary the field current IF to control this particular motor or to control the torque developed by the motor. You can take the same scene here, sorry, you could take, yes, you could take this way, load, and there may be a disturbance on this particular thing, on this particular load TW or NTW as you may like to take. This is Tm is the torque developed by the motor. So, in this particular case this torque is dependent on the field current, since I am keeping the armature current constant. I am giving this particular derivation to highlight as to what are the applications of field controlled motor vis-a-vis armature controlled motor. If you have to make a selection for a particular application, if you have to make a selection of an actuator, which of the two you will select? This is an important point and I need your attention on that point. But before I discuss that point, a quick derivation of the mathematical model of this. I will not write the equations now. I can, I hope, give the block diagram directly. Okay? So, in this particular case, the armature resistance, the field resistance and field inductance, both the parameters I am taking, because the field inductance is not negligible. Okay? So, in this case both the parameters are being taken and EF is the voltage which is the controlling voltage which controls the torque. So, come on, make a diagram. EF is the variable here, there is no back EMF facing EF. So, I can put a block directly, that block is 1 over RF plus SLF. This gives me IF, the field current here. Now, this IF multiplied by a torque constant, let me put it KT dash only to differentiate it from the earlier torque constant. Since in this particular case the armature current is constant, so the torque is directly proportional to the field current. So, this gives me the value of the torque Tm. At this particular point I can add NTW algebraically, which is the disturbance torque. This is the net torque available for driving the load, and here I can put the load parameter 1 over Js plus B, I get the value of omega. You will please note that in this particular case the so called electric friction effect is not available. Okay? The electric friction effect, the damping effect you had in the armature controlled mode is now not available, you are controlling it through the field current. And in this particular case the mathematical model, one more point, turns out to be a third order model. Between omega and EF, what is the model? Between omega and EF, please note that I can write this as Km dash only to differentiate it from the earlier value Km divided by, I think it can be directly written now, tau f s plus 1 into tau m s plus 1. This is a second order model, but if I take the relationship between the position theta m and the voltage EF, it becomes a third order model. You see that the higher the order of the model, more complex will become the design, as you will see later. In this case LF cannot be neglected. Okay? So, between omega and EF it is a second order, between theta m and EF it is third order. Tau f, as you see in this particular case, is LF upon RF, which is the field time constant, which is not negligible, while the armature circuit time constant was negligible. And tau m is identically the same, that is, it is the mechanical time constant as you had in the earlier case, but now in this particular case in the mechanical time constant the Kb term is not coming. Okay? So, this becomes the mathematical model. Now, as I said that, I will like you to understand the point as to how this selection is made, as to which motor you should take for the purpose of control when a particular application is given to you. So, as far as the field circuit is concerned, you see the great advantage is this, that the power amplifier in this particular case will be, the requirement on the power amplifier will be low, because the total amount of power required to drive the field circuit is lesser than that required for the armature circuit. So, the controlling unit, the power amplifier in this particular case is going to be less costly. Okay? So, the price you are going to pay in terms of the performance of the system is when you look at this circuit. You see, it requires an armature current constant. Now, keeping an armature current constant, if there is a requirement of high armature current, is very difficult. What you will normally do, what you will do, in a circuit. How will you keep the armature current constant? You can keep the armature current constant by using a high volt constant voltage source. If the resistance of this circuit R is reasonably larger than the resistance of the armature circuit and this voltage source is high, in that particular case please note that your IA is more or less constant. It is because why the IA should change? The IA changes because of the back EMF effect. Now, this back EMF effect is going to appear as far as the armature side is concerned, and because the back EMF will change with speed, the armature current cannot be kept constant. But if you take a large voltage source here and a large resistance here, in that particular case the armature current can roughly be kept constant. However, this particular approximation will be more correct if the requirement of the armature current is not very high, and therefore I can conclude my discussion with the statement that field controlled motor is a good competitor for selection as far as low power servos are concerned. Wherever there is a low power requirement, so that the armature current IA will be low in that particular case, and it will be possible to maintain that current at a constant value reasonably well. For a high power servo, you see, it is the armature controlled motor which is used, and I can conclude my discussion on the motor with the statement that in most of the industrial control applications, it is the armature controlled motor which is used and not the field controlled motor. Because of its other advantages also, you have seen that it gives you the advantages of damping as well, and a proper control is possible within the armature controlled mode. Okay. The trends in technology, I think it is quite appropriate I could mention here as far as the motor drives are concerned. Though I will not go to the details of this, the trends in technology are to take care of the problems associated with these motor drives. Come on, can you suggest what could be the problems associated with these motor drives? Well, one of the problems, the major problems which has not been visible in our discussion, is because of the brush friction. You see that the brush friction will make your mathematical model a non-linear model. You have happily taken it to be a linear model, taking the friction to be viscous friction only, but the brush friction is a constant frictional source, and if you add a constant friction into the system which is independent of speed, your mathematical model becomes a non-linear model, and the total analysis which you are going to make on the assumption of linearity may not be valid. And therefore, this is one of the great assumptions we are going to make in using this particular model. And the latest trends in technology are to give you brushless DC motors. In that particular case, the commutation is electronic. So, it means now brushless DC motors are available, so that the linear mathematical model is valid and non-linearities due to the brush friction are taken care of. One more problem you see which we have happily ignored, and that problem is associated with the gears. We have taken the gears to be simply a linear relationship given by the gear ratio. Unfortunately, the situation is not that simple. You see that the two gears are in mesh. Okay? When the speed reverses, what will happen? The reversal of the gears will not take place instantaneously, there will be a backlash, and the backlash in the gear reversals is going to introduce another non-linear term, and therefore, in the gear drives, the mathematical model which we have derived is not again applicable, it is only an approximate analysis. That is, the equivalent reflection on the motor shaft is based on the assumption that the backlash is 0, which is never the case. Okay? So, it means, well, you should understand the limitations of our mathematical model. Well, nonetheless, still the mathematical model which we are going to use are giving useful results even under these assumptions, but the technology is taking care of these problems. Now, the direct drive motors are available. In this particular case, the requirements of torque and the speed are taken care of in the motor construction itself. You recall my statement that we required gear train for torque magnification and speed reduction. These requirements are taken care of in the motor construction itself, so that the direct drive motors directly can be interfaced to the load without the need of gear trains in between. The advantages being very clear in that particular case, the nonlinear problems of backlash or friction in gears etc. will not appear. Okay. Yes, please.
So when will the speeds reverse and what conditions? You said that there will be a backlash because the speed will change direction and the rotation will change direction.
Right.
When will that happen, sir, in DC machine?
Well, when will that happen will depend upon your application. Will you not require bidirectional control? You see, you think of antenna control. Your motor is controlling antenna. So your antenna control will require, you see, your motor is moving in one direction. Your control signal now requires that the antenna should track the torque in the reverse direction. So it means immediately the motor will have to reverse its speeds, and hence a bidirectional control will be required. So there are applications in industry, unidirectional control and bidirectional control, both the applications are there. Wherever bidirectional control is required, the reversal in the direction of motor rotation will be required, and that reversal will be provided by the controlling voltage, and hence the backlash will appear. Is it okay? Okay. With this now, I think I can come to the position control system. With this introduction about the motor, I can come to the position control system. Now look at this system, this position control system. An idea of the position control system was given last time also, but now let us have a complete discussion how the system works. In this particular case, you will note theta L is the attribute of interest. This is the variable you want to control. Look at the arrangement I have shown, which is not a unique arrangement. It is a symbolic of the arrangements normally employed in industry. You can use different hardware as well. Theta L is the attribute of interest. Let us say it is the antenna position. Theta R is the position, is the command signal. In this particular case, symbolically, the command signal is being given by setting a wiper on the potentiometer, but in an actual practice this command signal may be coming digitally or may be coming through any other device. You see that it is a symbolic arrangement that you are changing the wiper on the potentiometer, and hence a voltage here which is proportional to the position theta R is coming at this particular point, and let me call this voltage as ER, which is the reference position. So the relationship, you see, in your minor also these relationships were required. Relationship between ER and theta R is through a potentiometric constant, and that constant depends upon the voltage source over here, that constant depends upon the resistor used over here. Okay? But let us capture it in a single constant Kp, so that ER is equal to Kp into theta R, a voltage proportional to position is available. I am mentioning this point again. I am worried about ER and not the way it is generated. It is only a schematic arrangement to generate it. It will depend upon the application and the way the signal is being generated. Similarly, the output. Well, the output simply I am showing it here through a potentiometer. You will please note that a potentiometer again leads to nonlinear problems, because it has a finite resolution. A wire wound potentiometer, for example, will only change step by step and will not give you a continuous movement. So in that particular case, a potentiometer is also adding to nonlinearity, but in my mathematical model at this point I am neglecting that nonlinearity, and I am assuming a linear relationship between this voltage and this particular position theta R. At a later stage I will come to other devices which are better than potentiometer in terms of the linear behavior and which are more extensively used than the use of potentiometer in industry. But a symbolic arrangement, a schematic diagram could be taken at this stage, as if I have a device for generation of the reference signal and I have a device for a generation of the feedback signal, and these two devices, these two potentiometers could be replaced by better devices. Okay? Those better devices will come up later in our discussion. But at this point now I have a voltage E naught, which is the feedback voltage which depends upon theta L, and I have a voltage ER which is the reference voltage which depends upon your command. Okay. Now look at this op amp circuit. this particular op-amp is giving you a voltage which is proportional to ER minus E naught. So, it means it is acting as a differential amplifier with gain RF minus R. I will give you the block diagram, but first let me scan it all through. The gain is minus RF by R and it is a differential amplifier because it is giving you a signal ER minus E naught. Okay? Well, one point at this stage itself you may please note, here as far as this wiper is concerned, this is on the negative side and this wiper is concerned, I have deliberately connected it on the positive side. Okay? You will please note in that case, ER is a negative voltage and E naught is a positive voltage, and this particular gain is minus RF by R. I hope you won't mind if instead of showing negative signs with ER and E naught, I take this block diagram, ER plus minus E naught, and here I am putting RF by R. It is an equivalent scene. Please see, I have taken this particular block diagram to represent the phenomena. E naught I have taken onto the positive side, ER I have taken onto the negative side, and this differential amplifier has got the gain minus RF by R. So, minus signs appropriately taken care of, this gives you the block diagram. I hope this is okay. Fine. And in this case now, let me put a Kp here, Kp, a potentiometric constant, and therefore this becomes theta r. Let me put a Kp here, a potentiometric constant, and here is the value theta L. So, I will connect theta L to the circuit, but this theta L into Kp is E naught, and this can equivalently, this Kp can be taken into the system, so that your input is theta r here directly plus minus, this is theta L here, so that this becomes system error. So, I am heading towards a unity feedback system if I take this arrangement, and your Kp in that particular case can be taken as Kp RF by R. This, if I complete the block diagram, is going to give me a unity feedback system. Okay? I hope this point is very well understood. Okay, let us go back to the diagram. So, it means I have reached this point. At this particular point, I have a signal ER minus E naught multiplied by a constant, that is the gain of this differential amplifier. Now, I need your attention at this point. What I am doing here is that in addition to this signal, I am taking another signal which is coming from a tacho generator. This tacho generator, this again the signs, I need your attention on the signs also. This tacho generator voltage is ET with a negative sign. So, it means this particular amplifier is again working as a differential amplifier with gain minus RF dash by R dash. And what is the input? The input to this amplifier is this voltage. This voltage you could name, you could give some name to this particular voltage. Let us say E dash, I say. This E dash minus ET multiplied by RF by R dash with a negative sign will be the voltage available at this particular point. So, it means now you are going to have two loops, it should be clear. One is the primary loop, which is the feedback of the position, and this is the secondary loop or the minor loop, which is the feedback of the velocity. So, it means I am feeding back the velocity in addition to the position as far as this total feedback control system is concerned. Now, you will note again the manipulation, so that the negative sign is taken care of. This is my power amplifier. What is the gain of the power amplifier? The gain of the power amplifier is again with the minus sign RFP divided by RP. So, what I can do is I can take the total gain here as the gain, two gains multiplied, and the negative sign is automatically taken care of, and hence I take you to the block diagram. The minor loop side I completed this way now. This was the signal, we named it as E dash. Let me put it a plus sign here, a minus sign here. This is the signal ET coming from the tacho generator. This particular signal I multiply it by RF dash RFP divided by R dash into RP, so that this becomes EA, the armature voltage. This point, since on this slide there will not be a space, so from this armature voltage I will continue with my block diagram, but keep in mind that I will have to generate signals Et and theta L, so that the complete block diagram can be drawn. So Et and theta L I will generate from a block diagram which I take as a continuation from Ea. So this Ea has come at this particular point. Now I am here. Ea is the voltage which is available to the armature. This particular voltage, the complete block diagram can be drawn, and hence I think yes, this will be appropriate here. Theta r, theta L, a constant K1 plus minus another constant K2. Here let me take motor. I think this now can be drawn this way without any problem, and this is theta m. The motor relationship you will be able to draw, and this you know that as far as the transfer function of the motor is concerned, the transfer function of the motor is Km divided by S into tau m S plus 1. You can complete this block diagram through the feedback loop, which is the back EMF loop. Okay. So I am not taking that, I am taking this as a motor and generating Kt and generating Kb and theta L. Help me please, how do I get this value Et from theta m? Give me the value of this block, I need your help now. Give me the value of this block so that I get Eb here, the back here. Oh, I am sorry, I needed Et here, the tacho generator voltage. Yes, what should be the value? SKT. Kt is the tachometric constant. Because the tachometer output Et is proportional to speed, and in the block diagram I am tapping my signal from theta m. So this becomes theta m into SKT. This is Et and this is the feedback signal available over here. Now you want a signal theta L as well. So if I want a signal theta L, so in this particular case what I will do is, yes, give me the value here as well please. N is the gear ratio. What should I put over here? Should it be N? Yes. N we had taken, if you recall, theta L by theta m, that is right, it will be N. N we have taken as theta L dot over theta m dot, so I am writing it here so that there is no confusion. N I am writing as theta L dot over theta m dot. This is the ratio. If I take this as the gear ratio, then it will be N, and here it is the load position theta L. From theta L you tap your signal and take it to this particular point. This becomes the complete diagram, where the motor block could be again written in terms of a total feedback loop, and therefore this motor block will give you one more feedback loop. However, that feedback loop is not because of us, that is, we have not added a component there. That feedback loop is because of the inherent nature of the motor, which is through the back EMF. So if I want to take this feedback loop also from theta m, if I tap a signal, S into Kb I will put, and suitably that particular block will be completed over here. Okay. Now here, before I let you go, I like to pose a question. If I break this particular loop, what will happen as far as the functioning of this system is concerned? If I break this loop, what will happen to the performance of this particular system? Yes, I will need a reply from you only. You just see that there are two loops. One loop is through the position and the other loop is through the velocity. That is, you can say as if this particular loop is the derivative of the position. So it means as if in addition to the output signal, you are feeding back the derivative of the output signal as well. So if this derivative is removed, if only the output signal is fed back, what will happen to this particular system?
So there will be more hunting.
It means basically, I think the point is right. Basically, it will continue to act as a position control system. The only thing is this, that this Kt, by proper use of Kt, you are controlling the damping of the system, because this is also controlling the damping. A derivative feedback, please see, like back EMF, the derivative feedback is also controlling the damping of the system, because after all you are giving a signal which is proportional to speed. Back EMF is also a signal which is proportional to speed. The only difference between back EMF KB and KT is this, that the back EMF KB is beyond your control. Once the motor is selected, you cannot change the value of KB. But KT signal is in your control, because once the motor is selected, the selection of a tacho generator is in your hand, and therefore the signal KT can be controlled. But you should please note that in this particular block diagram, KT serves the same purpose as KB, the only difference being that KB is not in your control once the actuator has been selected, while KT is in your control because the feedback measurement device you can appropriately select. Okay? So it also provides damping. As he has rightly pointed out, if I remove this particular block, that is, if I do not give the feedback signal from the tacho generator, the motor still acts as a position control system. The only thing is that the performance of the system may get deteriorated. Okay? The last question, let us restore this particular block, restore this and break this. Yes, very important point. Break this. Keeping this in mind, actually it is a voltage ER, and this is a, this of course you have broken, so this signal is not coming. The reference signal is actually a voltage which has been appropriately interpreted as proportional to the required position. Now this is the last question, answer this question and go. That is, if I break this loop and this loop is there in the system, the same system was working, was there, as how would this system will work and what will be the nature of the performance of the system? Yes.
Speed control.
Yes, please write. It is right. Please see that your original position control system now is a speed control system. This theta r is not important, you see. This is the voltage which earlier was interpreted as a signal proportional to position, because a feedback of position signal was coming. Now this particular voltage is actually representative of speed, because there is no position feedback loop. So this particular voltage ER, which is going in the forward loop, is a representative of speed now, and a speed feedback is coming in this particular case. Please see if this loop is broken. If in that particular case the primary feedback loop is that of speed, and therefore the system acts now as a speed control system. Okay? In this particular case, this theta m into SKT is actually coming as from omega m, that is the motor velocity, and this particular signal is KT in this particular case. Therefore your KT into omega m becomes the feedback as far as the speed control system is concerned. So once this primary loop is broken, the feedback is that of speed, and this voltage is interpreted as a signal proportional to speed, and hence the resulting system becomes a speed control system. That is all. Thank you.